Good morning. So in this talk, I'm going to put in the context BDAS stack of warehouse scale computing. And I am Stoica. I am a faculty here and one of the co-directors of the AMPLab. So in this talk, I have three goals. First, I am going to follow up on Mike's presentation and summarize our workload assumptions. Second, I'm going to discuss the hardware trends and the implication on our software stack design. And finally, I'll provide an overview of the BDAS stack and of the main components you are going to hear about over the next 2 days. So what do people use big data for? Well, first, they use it for creating reports to track or better understand business processes, transaction, or things like that. Second, they use it to diagnose and answer questions such that why is user engagement dropping, why is the system slow, or maybe detect spam, worms, viruses, or DDoS. And finally, and most importantly, they use it for making decisions. For instance, what new features they have to add to their product, and the classical example to decide what ad to show to a particular users, or once they identify, say, a spam, to block it. So as a result, the design of our software stack is driven by the belief that the data is as useful as the decision it enables. So what does this mean? Well, this means that we want low response time on historical data, since faster we can make a decision, the faster we can make a decision, the better. We want the ability to perform queries on live data, since decisions on real-time data are better than on a stale data. And finally, we want the ability to perform sophisticated processing on large volumes of data, since the more data we process, at least intuitively, the better decision we should be able to make. So next, I'm going to move to the second part of my talk, and that is to look at a little bit at the hardware trends and of the impact of these trends on our software design. So if you were to buy a new cluster today for data analytics, this is how a node will probably look like. So you are going to have, for each node, or each server, 1 or 2 CPUs, so an aggregate of 8 to 16 cores. The transfer rate to the memory, assuming a quad-channel DDR3, like in Sandy Bridge, around 40 gigabytes per second, 10 gigabytes per second per channel. You'll have probably between 64 and 256 gigabytes of RAM, and somewhere between 8 and 12 disks, each disk with a capacity between 1 and 3 terabytes, and a transfer rate between 50 and 100 megabytes per second. Furthermore, this node, this server, will be connected to a top-of-rack switch through a Ethernet, typically 1 gigabit per second, or more likely today, 10 gigabits per second. The top-of-rack switch will have an aggregate capacity between 4 gigabits per second, or again, more likely today, 40 gigabits per second. So for most traffic patterns today, 2 nodes in the same rack will be able to communicate at full capacity, full bandwidth, most of the time. Now, if you go across the rack, how much bandwidth you are going to have, it will depend on the network architecture. If you have a more traditional hierarchical network architectures, then your capacity going when you go across racks will decrease, maybe even by a factor of 10. However, if you are looking at the new trends in network architectures in data centers, you see that there are many designs and actually deployments which provides full bisection bandwidth. And in that case, actually, 2 nodes, they can communicate across racks, and they get their full bandwidth, 10 gigabits per second. You may also want to add to some of the nodes, at least, some SSD drives. An SSD drive typically today, SATA drive, has between 256 and gigabytes or 1 terabyte. The transfer rate will be somewhere between 255 500 megabytes per second. Again, here I'm assuming a SATA 3 interface. And therefore, if you put 4 SSDs, you are going to get an aggregate storage between 1 and 4 terabytes and an aggregate transfer rate between 0.8 and 2 gigabytes per second. So to put things in context, it's interesting to understand, if you have $1,000, how much you can buy when you look at all these storage options. And what you can get with $1,000 today, you may be able to get between 15 and 20 terabytes disk storage, $1,000, assuming consumer-grade disks. Or you may be able to get 1 terabyte of SSD storage, assuming a SATA disk, or as much as 200 gigabytes of RAM. Okay, so as a rule of thumb, the SSD, the price per bit of an SSD, it's 5 times lower than of RAM, and the disk price on byte is a factor of another 20x lower than of SSDs. Okay. So now next I'm going to switch gears and talk about the storage capacity and the transfer rate trends. So for memory, everyone knows the capacity doubles every 18 months. So this is basically the Moore's law. This is also holds more or less for the hard drives. Actually, based on some data, it doubles a little bit faster. And also is true for SSDs. The capacity doubles more or less according to the Moore's law every 18 months. In the case of the CPU, as everyone knows, the frequency is no longer increasing. So to improve the performance, the way to improve the performance is to increase the parallelism. So far, the number of cores per chip doubled every 24 months. As we go forward, actually it seems that this growth will slow down. And now let's take a look at the transfer rates. So the network I/O is doubling every 24 months. So in this plot, you see this red line, which represents the network I/O trend over years. The memory bandwidth, assuming here I am looking at DDR memory, is doubling every 36 months. And the SSD, assuming again a SATA interface, the transfer rate doubles every 36 months. Okay, so everything here doubles, over some time interval. One of the exceptions is the disk bandwidth, which increases very slowly. Okay, so to summarize, if you look at all the storage types you have in a server, all of it more or less doubles, the capacity doubles every 18 months. And if you look at the transfer rate, in the case of network I/O, memory bandwidth, and SSD SATA bandwidths, they doubled somewhere between 24 and 36 months. Again, one exception, it's the disk bandwidth, which increases much slower. And finally, like I mentioned, the number of cores on a CPU doubles, at least used to double every 24 months. In the future, will be a little bit slower. So the storage is cheap and capacity increases exponentially. At the same time, most of the transfer rates increase exponentially, but slower. So what does this mean? There's a gap between the capacity and the transfer rate also increases, and is going to continue to increase in the future. And actually, this increase will be also exponential, but a smaller exponent. Now, there are ways to alleviate that. We can add multiple channels or multiple disks to get a higher aggregate throughput, but this does not come for free. For instance, when you do disks, if you want to use this striping to increase the aggregate bandwidth to the disk subsystem, you need probably to increase the block size. And also, you are more vulnerable, the performance is more sensitive to any single disk getting slow or failing. So basically, this means that the data center application and software must to carefully select where to place computation and data. And this will be more and more important in the future. Still, based on all the data I provided to you, the main challenge it's accessing the disk. It's very slow. Today, if you want to read or write 100 gigabytes of data to or from the disk, it will take you at least 1,000 seconds, okay? A lot of time. And things are only going to get worse. The transfer rates are not increasing that fast. The memory is going to continue to increase exponentially. So for instance, in 1-2 years, you are going to have 512 and maybe even 1 terabyte of RAM. So just to populate that RAM from the disk may take hours. And actually, it will be much faster to access remote memory. And SSD could be a solution. However, they are not widely deployed in the data centers. So that was a challenge, actually. But actually, there are also opportunities. If you look today, just a few node clusters, so say 4, 8 nodes, may have over 1 terabyte of RAM. And 1 terabyte of RAM is enough to handle many large data sets. Just to take an example, if you have 1 billion of users, and not many of services have 1 billion of users, you can accommodate 1 kilobyte of data per user. That will fit in 1 terabyte of data. So the other aspect is that the number of cores increases, has doubled every 24 months. But even with that, because the memory doubles much faster, increases much faster, you are going to have a lot of more memory per core in the future. So this means that judiciously using RAM is a key to support the new data analytics workloads. Okay? Now, existing OpenStack like Hadoop is mostly focusing or has mostly focused on disk data sets. And this was great. It allows you to process massive amount of data and use sophisticated algorithms. It will just be slow. So one of the key properties of our software stack is that adding RAM to the mix. So by doing that, we enable interactive queries and data streaming. Actually, as we are going to show for real application, we can achieve a speed up of 30x over running the same query, the same computation on today's data stack, open data stack. It also, because it gives now, we can do a lot of more queries, perform a lot of more queries, a lot of more computation during the same amount of time, right? 1 order of magnitude or more. This dramatically increases the ability to explore and data mine the data. It will provide a qualitative difference in understanding your data. Now, we are not going to talk much about SSDs during this AMPLab, but rest assured, we are looking seriously into those, and we probably are going to have something to say about them as the next AMPLab. So our BDAS stack leverages the open source ecosystem, including HDFS and Hadoop, and is doing that by adding new abstraction to take advantage of storage hierarchy, in particular of memory. And specifically, it provides this resilient distributed dataset abstraction, or RDDs. You are going to use quite a bit about it, which allow users to reliably store data into memory, and also to control the way it's partitioned, such as to minimize the communication. In addition, we have built Mesos, which is a management platform that enables multiple frameworks to share the cluster resources as well as the data stored in HDFS. And we do this through these resource offer abstractions. We basically virtualizes the resources of a node in the cluster. Finally, we simplify parallel programming, for instance, by providing Scala interface to Spark. And we also built Shark to enable and to give the ability to the users to use SQL-like queries to mine the data. So over these next 2 days, you are going to hear mainly about 3 projects: Mesos, Spark, and Shark. And these are three key components of our today's data stack. And Mesos and Spark, we have started these projects in 2009, and we open source in 2010. And Shark has started last year, and we have an alpha release earlier this year. Our software stack, BDAS, it's used at different companies today. Some examples here are Twitter, Foursquare, Cloud, Quantified, Conviva, and so forth. And next, let me move on and talk about put the BDAS stack in the context of today's open analytics stack. So today's open analytics stack consists of two layers. The first layer is storage layer, which is implemented by HDFS. And on top of that, we have a framework layer. For data analytics, we use this Hadoop stack, which consists of Hadoop itself and many other frameworks which runs on top of Hadoop, like Hive and Pig. And then there are other frameworks like Storm, which gives the ability to provide stream processing, or MPI, which is, as you know, is the de facto standard for data processing and modeling in high-performance computing. So now, in this software stack, we add a new layer, resource management layer, in the form of Mesos. So Mesos is a management platform that allows multiple frameworks to share the cluster and the data stored in HDFS. So basically, by having a small shim layer for the existing frameworks, we allow these existing frameworks to run and their application to run and share the same cluster. So you can have on the same cluster running multiple HDFS instances, different versions, or you can have Hadoop running side by side with other frameworks like Storm and MPI. In addition, we built new frameworks. The first framework we built was Spark. And like I mentioned, the Spark is an in-memory processing framework which enables iterative computation and interactive queries. Then more recently, on top of it, we built Shark. So the way to think about Shark is Hive on top of Spark. And basically, it's backward compatible with Hive. So it allows you to run unmodified Hive queries. But now the queries will be interactive as long as the data fits into memory. Now, more recently, we are starting to add streaming capability to Spark. And we call this new framework Spark Streaming. And Spark Streaming, as the name suggests, provides large-scale streaming processing while handling the failure transparently and efficiently. At the same time, Spark Streaming, we believe it's the first framework to unify the streaming batch and interactive computation models. And this is a features we are pretty excited about. We plan to have a release, alpha release of Spark Streaming later this year. And tomorrow you are going to hear a preview from TD on Spark Streaming. Last year, we also started to build a new framework, which is called BlinkDB. We are not going to talk about it during this AMPCamp. It's still in development. But just to give you an idea, the BlinkDB provide bounded errors and bounded response times on very large data. And this is one of the first frameworks which tries to enable the users navigate the trade-off between the cost, the quality of the answer, and the accuracy of the answer, the trade-off that Mike was talking about. So fundamentally, BlinkDB will allow the user to specify an error bound, and the system will return an answer as fast as possible, or to specify the time, and the system will provide an answer with the best error bound it can. Okay. Finally, as I said, the methods allow multiple frameworks to share the cluster resources as well as data stored in HDFS. However, as I mentioned before, we believe that other storage medias, such as memory, will play an increasing important role in our stack. As a result, we introduce another layer in the stack, which is a data layer, that will enable frameworks not only to share the data stored in HDFS, but also to share data stored reliably in memory, and in the future also to share intermediate computations or partial results. This layer is under development, and the working name now is T-Rex. So in summary, over the next 2 days, you are going to hear about our first iteration of the BDAS software stack. In particular, you are going to hear mainly about 3 components. Mesos, which enable multiple frameworks to share cluster resources as well as the data. Spark, which enable users to query data interactively and write interactive computation, such as machine learning algorithms. And we achieve that through the use of RDDs, which provides an in-memory reliable abstractions for the application. And finally, Shark, which allows the user to run Hive queries interactively on data, which of course fits in memory. As we look to the future, we are fully committed to develop a stack that allows the users to trade between the answer quality, response time, and the cost, as Mike has mentioned in the earlier presentation. And one thing I also want to add is that in developing this stack, like probably was already clear in my presentation, we are committed to be fully compatible with all the open source standards out there. Thanks. If you have any questions. Okay, so I think then we have a break now.